Log on, tune in, find out. Another good idea from Cambridge.
We will speak about the spectrum of large non-hermitian random matrices.
Okay, thank you, Frank. I'm very glad to be here. So I'm going to speak about non-hermitian random matrices. Nowadays, the theory of Hermitian random matrices is most of the open problems in this field have been solved, especially recently with the work of Erdos, Lai-Niao, and Tao and Wu. And there has been a lot of work and nice ideas in the world of Hermitian random matrices. And concerning the non-Hermitian random matrices, there are much less is known, and there is two main reasons for that. The first one is that probably it's slightly less interesting because there is no real physical interpretation about what an eigenvalue of a non-Hermitian random matrix is. And also there is the geometric interpretation of an eigenvalue is less obvious. So what do we talk about? So we consider an n by n matrix, okay? And counting multiplicities, we will look at its eigenvalues, okay? And what will play an important role also is are the singular values of this matrix. So the singular values, they are positive, okay, and they are the square roots, they are the eigenvalues of square root of xx star, okay? So they are the square roots of the eigenvalues of xx star. And the singular values have a nicer geometric interpretation than the eigenvalues, because if you look at the unit Euclidean ball, okay, and you look what your matrix X maps it to an ellipsoid, okay, and the direction of the ellipsoid are precisely the eigenvalues, the singular values, okay, and while the eigenvalues, they could be like that. Okay. So in this talk, I will mainly be concerned about what is called the global spectrum. So what does it mean? So I will just mention results about the empirical distribution of the eigenvalues. Okay. Okay, so from the eigenvalues, you build a probability measure, which puts mass 1 over n for each eigenvalue. Okay, and we can define similarly so I will call this a spectral measure. Okay, or the empirical spectral measure. And we can do the same with the singular values. Okay, and we'll say this is singular values measure. Okay. So to motivate the sequel, so if we look at, for example, this matrix, okay, so this is a very famous example, but is mentioned in half of the introduction of talks on non-Hermitian random matrices. Okay, so look at this matrix. So this is a nilpotent matrix, so all the eigenvalues are 0. So this is the associated spectral measure is just a Dirac mass at 0. Okay. If you just put a 1 here. Okay, so you change one entries in your matrix. So what you are doing is just now your eigenvalues are on a circle. Okay, so you can represent it as a derivative graph along a circle, and it's quite easy to check that the eigenvalues are precisely the n root of unity. Okay. So when the size of the matrix goes to 0, this spectral measure converges to the uniform measure on the circle, while this one it stays as being the Dirac mass at 0. So you see, by just changing one entry of the matrix, you can change completely the behavior of the eigenvalues. And this is not the case for Hermitian order matrices, because for Hermitian order matrices, or more generally for normal matrices, we have inequalities like Huffman-Widlands inequalities, which tells you that you can bound the difference. You have bounds like if A and B are, let's say, Hermitian order matrices. The Huffman-Widlands inequalities tells you that you can bound this in terms of the Frobenius norm of your matrix, of the difference of the matrix. Okay, so if you put one overhead here, so this is a normalized Frobenius norm, and this is the L2, that's the square L2 Wasserstein distance between the measure mu A and mu B. So you whatever it is, the only thing important is that by just, if A minus B is the difference between two matrices is small, then the spectral measure has to be close. And of course, due to this, this kind of inequality does not hold for non-Hermitian. Okay. So that's just some motivation. So I will speak about random matrices. So we will take a probability model for the entries of for the entries of the matrix. So the basic model is just to take you take a collection xij of iid random variable. So they are independent and they have the same law, and they are normalized. That's the average is 0, and they have a variance equal to 1. Okay, it can be complex or real number. We don't care. And so we can ask now in this setting when we take the n by n matrix. Okay, so I will often skip the n index. Sorry. How those behave as the size of the matrix grows large, the spectral measure, the empirical spectral measure, and the singular value measure. Okay, so the basic theorem in the field is the so-called circular law theorem. Okay. So let's first start with the singular values. Okay, what happens to the singular values? This is known for a very long time. It is due to Marchenko and Pastur. In 1967. They prove that when you take this matrix, okay, so it's an n by n matrix, you divide all entries by square root of n. This measure, this probability measure, so it's a probability measure on R plus, converge to a limit measure. Okay, so, and this convergence is almost sure. So for those who are not very familiar to probability, just say that if you take any continuous function with compact support, for example, the integral of f d mu of x square root of n converge to the integral of f. Okay, and this has an explicit expression. It's 1 over square root of pi of so this is only, so what is this? It's called the quarter circle law, because this is just a quarter circle. The density of this measure is just a quarter circle of radius 2. Okay, so this was in 1967. And for the behavior of the spectral measure, due to the difficulties associated to eigenvalues, there is the final statement. So the first one who gave a non-rigorous proof is Gierko of the statement, and then there was a first rigorous proof by Bai, but the final version is due to Tao and Wu. Nearly 40 years after, more than 40 years after the result of Marchenko and Pastor, and they prove that almost surely the limit spectral measure converge to the uniform distribution on the unit complex disk. Okay. Okay. So this is the basic theorem. So what does it tell you? Apart from the beauty of this uniform distribution. So for example, if your matrix A is normal, when A star is equal to A star A, then it's the eigenvalues are the absolute values of the eigenvalues are the singular values. Okay. If we look at 1 over n of the sum for one, the empirical measure obtained by the absolute values of the singular values of the eigenvalues. Sorry. From this result, this one, we know that this converges to a distribution which is like that. 0, 1. Okay, it's just the integration of the absolute value of the uniform distribution on the unit disk. Okay, so we see that between this shape and this shape, it's very different. So from this we can see the asymptotic non-normality of the non-hermitian random matrix. Yes, why the square root of n? There is nothing fancy with that. It's a one-line computation to guess that this should be square root of n. If you try to compute, for example, the integral of x squared of this, so by definition, it will be 1 over n. So the sum of the square of the singular values of your matrix X, and here I can put a square. Okay, but this is by the spectral theorem. This is not nothing. The 1 over square of the trace of x square of x star x, and this will be 1 over square times the sum of yj of modulus of xij square. And since I have the law of large numbers, tell you that this converges to 1. So you have to put a square root of n to get something which does not explode to infinity. So this scaling, there is nothing magic about it. So since there have been a few developments around this circular law, so this is called the circular law. It's a bit misleading because this is the uniform law on a disk, but this is called the circular law, and this is called the quarter circular law. So for those who know, there is also a semicircular law in the jargon of random matrices. Just to motivate the sequel, I will mention two results which of around this property. So for example, what happens when you relax this assumption that the square that the variance is finite. Okay, so for example, what happens if the probability that your variable is larger than t is equivalent to t minus alpha, where alpha is a number between 0 and 2. So in this case, your variable has an infinite infinite variance. Okay. Then there is also for the singular value part Benarous and Guillonnet in 2008, I think. They also prove the same, formally the same kind of statement. That your n by n matrix, now the correct scaling is n power 1 over alpha, converge to a limit measure nu alpha. And the only property, which is not explicit, but the only property that I am going to comment is the fact that the mass that this measure puts on minus infinity, minus t, t plus infinity, okay, is exactly the same as the mass given by the law of the entries. Okay. Last year with Caputo and Shafai, we proved also that the spectral measures was converging to a limit measure, but this time, which was radial, okay, and the density at a very strange scaling was equivalent to c power 2. So polynomial terms. So the only thing important here is probably this behavior, that the density, that the limit spectral measure of heavy tail on matrices have an exponentially decaying tail. So again, there is a very strange, there is a very different behavior of the singular values and of the eigenvalues. So again, this is a fact of very strong non-normality. We'll mention the last result, which is still a bit further away from the circular law, but very interesting. This is take a diagonal matrix with positive numbers. Okay? Yes, you have a question or?
This measure nu sub alpha isn't supported. It's what you quoted for Benarous Guillonnet. It's supposed to be you went the interval minus 0 to t, right?
Yes, it's at 0 plus infinity.
So when you write below.
Ah, yes, sorry. Yes, sorry.
It's positive.
Yes, sorry, yes, of course. Thank you. So if you take a diagonal matrix like that, okay, so if you form a matrix, if you take two unitary matrices, U and V, and you form the matrix U, D, V. Okay, so this will be a matrix whose singular values will be exactly the SI. Okay. Okay. So now you can wonder what happens if I think of D as fixed, okay, as deterministic, but I take U and V as being unitary matrix, which are sampled uniformly according to the R measure of the unitary group. Okay, so I could think about this matrix as a uniform matrix given that it has these singular values. Okay. So there is the so-called singular law single ring theorem. Which is due to Guillonnet, Krishnapur, and Zitouni. Okay. So so you take a sequence of matrix. So again, everything depends on n, but when s goes to infinity, that the singular values converge to a limit probability measure, f. Okay, so it can be, I don't know, like that. This is my limit measure f. They proved It's not exactly what they prove. They prove a slightly weaker statement, but let's say this should be true. That the spectral measure mu of X will converge to a measure mu which will depend only on F. Okay, and this measure mu is radial, and it's called the single ring theorem because it supports. It is supported on a ring, or this ring can be a circle if the inner circle can be 0. Okay, but so even if this function, this limit distribution f has many wells, okay, like I've sketched, there will be only one well in the limit spectral measure. So that's why it's called the single ring theorem. Okay, but all these examples are just to show that it's spectral measure of non-hermitian matrices are complicated and not very intuitive objects. So now I will come back to this and explain the strategy, a simple strategy to prove this theorem. Okay, so we will forget about these refinements. Okay, so in order to state a new result and to have new example, we will look at matrix of this type, so n by n matrix, okay, where X is my random matrix. I know that I have to scale it by square root of n, and M, K, and L are deterministic matrix. Okay. So these are I give you a sequence of n by n deterministic matrix M, K, L. And I want to look at this, what can I say about the spectrum of this? So when I take M, K, L as being identity, I have this case. Okay, when I take K equal L equal identity, I can think of M as being the average matrix of X, because my entries are centered. So I could deal with non-centered Hermitian matrices by dealing with this case. Okay, maybe more interestingly, I could try to look at the spectrum of k independent copies of my matrix, x1 times x1 up to xk. Okay, when these matrices are independent, recursively, I could try, if I have understood how behaves the limit spectrum of this, recursively I could make a guess on what is the I could prove what is the limit spectrum of this type of expression. Okay, maybe also we could look at something like that. Matrix of the type y minus 1 times x, okay, where y is also IID centered and with unit variance. Okay, this would correspond to generalized eigenvalues, because the eigenvalues of this, assuming that I know that y is invertible, of course, the eigenvalues of this will be the same as the zeros of this, okay, of this polynomial in lambda. And more generally, it is of it has some interest to look at zeros of analytic functions with values in matrices. Okay, but let's stick to this case. So these are the 3 examples that could be of interest. So I will state a theorem and then I will explain the proof. The time I will. So assume that there exists alpha such that the function x gives x power alpha is uniformly bounded for, I'm going to tell what I mean by that, for my sequence of matrix, the spectral measures of the matrix Mn. What does I mean by that? But by saying that the lim sup of x power alpha d mu n is finite. Okay? And the same with x minus alpha for the matrix which comes as product. Okay, so in particular it implies that for n large enough, zeros is not an eigenvalue, so my matrix K and L are invertible for n large enough. Then there is a second assumption that for almost all Z in the complex plane, if I take the singular values of K minus 1 and L minus 1 minus K minus 1, it looks awkward, but it converges to a limit probability measure on R plus mu Z. Then the spectral measure of my product, when I plug in my random matrix, converge to a limit measure, so it's almost sure. And this limit measure can be expressed only in terms of this mu Z. Okay, so I am not going to explain you in this talk how do you relate mu to mu Z, because it's already it would take a long time, and it's easily described with use of free probability and things like that, but I don't want to introduce. What I just want to emphasize in this talk is what is the main strategy to deal with this, or to deal with all the problems with non-Hermitian matrices. How do you prove convergence? I will just mention this case, which is quite nice. So we will see that when we take K as being y minus 1, we can apply the hypothesis of the theorem to y minus 1. But we will see that later. Or we could also apply it to product of independent matrices. But for example, in the case 3, so it implies that the spectral measure of mu of y minus 1x converge almost surely to a probability measure which, through stereographic projection, is a uniform measure on the Riemann sphere. Okay? This measure. And this is due to the fact that when the x and the y's are the entries, when the yij and the xij are Gaussian complex variables, IID, then it can be proved. So, in the Gaussian case, but the expectation of this for any finite n is this measure by using some symmetry argument. So this is a case where you use universality. You don't need to compute the limit because you know in a very specific case, exactly in the Gaussian case, what the average of this spectral measure is. And since you know from this result that the limit does not depend on does only depend on the first and second moment of the law of the entries, you have your convergence result. Okay, so if you are curious, I can explain you why this is true in the Gaussian case. It's quite cute argument, which is not due to me, but okay. So now I will explain the results. Okay, so in all the proofs, the single ring theorem, the circular law theorem, or the case of Ecole, or this theorem, the strategy is always the same. There is a single strategy that is known up to now to deal with this case. So we could summarize by calling it the Ecole hermitization trick. Okay. So you start from the formula that the absolute value of the determinant of a matrix is the same as the square root of the determinant of AA star, right? So if you look what it tells you that the product of the eigenvalues in absolute value is equal to the product of the singular values, okay, of the matrix A. If I apply this to A minus Z, the eigenvalues of A minus Z identity are lambda of A minus Z, and the singular values are, I don't know what it is. Okay, when I apply this identity to A minus Z times the identity. So I don't want to write identity. So if I take log and 1 over n, I deduce that the log of lambda minus Z d mu A is equal to the log, so this is integral over C, and equal over 0 plus infinity. Okay, so this is the trick. So here you have a kind of Rosetta Stone between something which is lives in the Hermitian world with singular values, with a nice geometric interpretation in terms of direction of ellipsoid, and here something that we don't understand. I don't, which are eigenvalues of non-Hermitian matrix. Okay, so the price is just that you have to look at understand the singular values of your matrix when you translate your matrix by Z for any Z. Why? Because this is called the logarithmic potential of a measure at Z, and of course the logarithmic potential will characterize the measure, because if you take the Laplacian of your measure, if you take the Laplacian of the logarithmic potential, you will find 1 over 2 pi times the measure in sense of distribution. Okay, this is just because the logarithm, when you take the Laplacian of the logarithm, you get the Dirac mass. Okay, so this characterizes your measure, and I have a dictionary to go from singular values to eigenvalues. So this is very simple, and you can summarize this in a theorem. In a lemma, no? So take a sequence of deterministic matrix AN, okay? So we want to make convergence of at the end I want to a result which says then the spectral measure of my sequence of matrix converges to measure mu. Okay. So if I want to use this, I will at least have to assume that the singular value measure converge. So that for almost all Z, this converges to a limit measure using. Okay, this will be compared to the 2i of my theorem. And the first point is, okay, a weak convergence, as I said, it's only integral against all bounded continuous functions. So the logarithm has a discontinuity. So I mean, it's not bounded. So you have to add another argument. So you have, and the minimal argument is uniform integrability. So you have to assume that the logarithm is uniformly integrable for this sequence of measures. Okay, so this has to be true for almost all of these. Then mu, the spectral measure converge to mu, and u of mu of your measure is exactly what you expect as being the logarithm of mu d mu dz. When you take the Laplacian of that, you get mu. So just for those who are not familiar with probability, or so uniform integrability, the minimal assumptions to guarantee that non-bounding function, when you know that you have weak convergence, converge. So this will be that for the limit as t goes to infinity of the lim sup in n of the integral, you integrate your function over all t okay, so when you plug f as being log, and this is uniform integrability. Okay. So there is one trick here in the lemma. It's not completely obvious because you have to check that the uniform integrability of the singular values implies the uniform integrability of the eigenvalues. And this is the only mathematical content of the lemma, and is due to, it comes from the Weil inequality. The Weil inequality tells you that the largest eigenvalues are smaller than the largest singular values, and the largest singular values are, the smallest singular values are smaller than the smallest singular eigenvalues. So in words, that the product of the largest eigenvalues are less than the product of the singular values. And since you know that when k is equal to n there is equality, it implies also that the product that the smallest eigenvalues are larger than the product of the smallest singular values. Okay, so this will imply on a log scale that the uniform integrability of the log for the singular values implies the uniform integrability for the eigenvalues. Okay, so nothing fancy. So this is called Weil inequalities. So now, if I want to, so the theorem, I will just mention the proof for when k equal L equal 0, equal identity. Okay, just to keep things simple. Okay. Otherwise, you have to use stupid inequalities, like noticing that the spectrum of this is the same as the spectrum of that, and okay. So let's assume that k equals L equal icon. So what we really care about is to understand the measure and the singular values of m plus x over square root of n. So if we want to apply Gierko trick, so the first point to I, so as I said, it's something in the usual classical non-hermitian matrices. So this is well known. And so there is a theorem which is usually attributed to Dozy and Silverstein, but can be proved also by using Voiculescu, a theorem by Voiculescu, which says that if, so you have your sequence of matrix mu n whose singular value measure converge to a limit measure. Let's call it rho. Then the singular value of m plus x over square root of n converge also to a measure which depends on rho. Okay. So as soon as you know that the term that you add converge, the singular value distribution converge, then by adding the noise, the random matrix, it will converge also. And to know the explicit, to express new row as a function of row, that's where free probability or resolvent fixed point equation comes into play, but I don't want to comment. So this part is known. So that's why the 40 years gap between the proof of Martin-Kopastur and the final proof of Tao and Wu for the circular law comes from this part. So that's why now I am going to discuss. So maybe here. So uniform integrability. So in order to check that it is uniform integral, it will be sufficient to prove that the function is uniformly bounded for some beta. Okay. So if you prove that this function is uniformly bounded, then since it's worse at the singularity at 0 and at infinity than the logarithm, it will be enough. Okay. And so you have the result, which is the uniform integrability. It says that if you have your sequence of matrix Mn, if it is not growing too fast, is uniformly bounded. If for some alpha this function is uniformly bounded for your sequence of singular values of your deterministic matrices, then when you add the random matrix, it behaves not too bad. It's uniformly bounded for. Okay. And the term and the beta, this value of beta depends on alpha, obviously, and is much worse than alpha, but we don't care at this level because we just want to check the uniform integrality of a log. So we are not very greedy. So there is a trivial part in this statement and a difficult part. The trivial part is to check that this term is uniformly bounded. Okay. For this sequence of measures, this is easy because still from this Weil inequality, it's not hard to check that if you integrate the spectral measure of a sum of two matrices, it has to be less than up to a constant factor to the sum of the spectral measure of the same function. So we can so we know already that so this means that we know already that we take A and B as being X and M. We know already that this is uniformly bounded. So we just have to check the uniformly boundedness of my matrix but we have already seen that this is bounded. We have already seen this. Okay. So for this part, you take beta as being the minimum of 2 and alpha, and you're done. In the statement, you also have to, your matrix B, or should we be M, will come from being products of this term. So you also have to detangle. At some point, you will also have to use this inequality. But when you take the product, the singular values of a product of two matrices, it also satisfies a kind of other inequalities. It's the same, but the conclusion is the same. Okay. So bounding above this is a trivial task. So this was the difficult part. And here, to do with, so when you want to show that the smallest singular values are not too small. So to do that, you cannot disentangle the deterministic part and the random part that easily. So here we call back Tao and Wu, and they have made the major contribution. And that's from this point that they could prove the final version of the circular theorem, circular law theorem. So they proved that the smallest singular value, so with always the same assumption, okay, is not too small, meaning that it is larger than n power, so this is tau and Wu. It is larger than n power minus c, where c is 1000, for n large enough. So, but this was not good enough. We also need a control on the singular values of all singular values. So they check that this is less than I over n, larger than I over n, for I which is not too small. And too small is n power 1 minus gamma, where gamma is any number positive between 0 and 1. It's true. For example, 0.1, whatever you want, or 1/2. It's true. Okay, so I will comment on this. And in the two other cases, the proof of for the heavy tail matrices or for the matrices of for the single ring theorem, what is hidden somewhere, the level of high technicality, is to try to prove the equivalent of that, which can be more complicated. But so I will comment on this because I will just explain why when you have that you can you have this in one line. Okay, so you want to deal with this term, so you want to compute to find a good bound for you want to bound this uniformly in n by a constant. Okay, so what you do, you divide, so you reverse your sum and you divide between, so the first n1 minus gamma term you don't know what to do, so you just put them at this level you don't know. So okay, so I've done nothing. So this one, you bound them by this. You get n power beta c1 minus gamma. And this one, you bound this by it, this one. So it is, I just do elementary things, and you get constant time. Okay. So of course, when you take beta smaller than 1 to guarantee that this converge, and beta C1 minus gamma less than 1, beta C1 less than gamma, it's okay. Okay, so what really was already hard was this. So what is hidden between behind these two statements? So one is quite the proof of one of the two is fairly simple. This is this one. So what is hidden every time? This is you have to control the distance between one vector of your matrix to an eigenspace, to a vector space, which will be typically spanned by the other lines, other columns of your matrix. Okay, so let's call this x1. So what is hidden between in this theorem is to give lower bounds on this. Okay, and this is due to the geometric interpretation I've given to you at the beginning. And then how you do that? In the case for the case of this B, you can do it. So and since the column of your matrix are independent, this vector is independent of this vector space. Okay, so you can think of it as being deterministic. And if you look at the map, which to a vector in Rn gives the distance of your point to to vector space W, this is a convex. And so by using concentration inequalities, and you manage to prove this and to lower bound this. But it is not very difficult to check that the expectation of the distance squared when W is independent of x1 is just the dimension of the orthogonal of W. Okay. So, and due to the fact that it's convex and you bound this and irregular, you manage to check that the distance has to be quite close to the square root of this. And that's how you do that. For this, it's much more difficult because you have to take the distance from one vector to an hyperplane. Okay, at least you have to go up to I equals 0. So you have to look at the distance between one vector to an hyperplane. So for example, if you take W as being E1 orthogonal, where E1 is the first coordinate, and if you imagine that your vector, your variable xi, xij, they are equal to 0 with probability 1/2 and 1 with probability 1/2. Then with probability 1/2, this distance will be 0. So you are in trouble to find a good lower bound of it. So here you have to use the fact that W is not any hyperplane. It's an hyperplane which comes from the span of n-1 eigenvariables. And that's where you have a nice additive combinatorics and inverse Littlewood-Ford type of argument. There is one case though where it is easy, is when the entries when the law of the xij have a bounded density. In this case, by a few lines, you can have a nice lower bound of this. Okay, so in the 2 minutes I have left, so there are many nice directions. The first one, but I mentioned in the single ring theorem there was a gap. Because Guionnet, Krishnapur, and Zetoni have managed to deal the equivalent of this, but they have not been able to manage, in general case, the equivalent of this. Okay, so if you take a R unitary matrix, it would be very nice if somebody could prove that with high probability, the smallest singular value of U plus given matrix M, so that's deterministic, which is not too large, it cannot be too small with high probability. So if you could prove that, a few results would follow. So because you have seen that from the beginning that we have used very heavily the independence of the lines of the matrix here. But when you take other random matrix ensemble, like this one, the R unitary, there is no independence, so this argument falls down at the very first steps. Also, even if you take, we don't know how to deal with, at least I don't know, if you take a general polynomial in X, not X but X squared, for example. Of course, you could have some problems, but it is not clear in which case you can lower bound the smallest singular value of a polynomial of a matrix. And okay, thank you. I think it's everything I had to say. Thank you.
So you stated a lot of theorems where you have convergence in distribution, and they're like quantitative theorems. So can you say anything about the rate of convergence?
Rate of convergence? Not really. What people have started to look at is so to try to go beyond this weak convergence is, for example, to try to prove. Well, if we come back to the circular law, so just the eigenvalues of, to try to prove that the max of the eigenvalue of the matrix if, so a square root of n, converge almost surely to 1, for example, which is not implied by the weak convergence. From the weak convergence, we know that the this lim is at least 1, but for example, you can prove that this is when you have high enough moments on the entries, when the moments of the entries xij are, let's say, 4 or 10 moments, finite. But for explicit rate of convergence, we don't know. For example, there is no, up to my knowledge, there is no central limit theorem, which is known. So, for example, take a function of the eigenvalues, and so what can you say about the fluctuation of this? So it's already quite complicated in the Hermitian case, and the regularity of the function f plays a crucial role. But in the non-Hermitian case, we don't know what to do with this problem. Maybe in the explicit, there is one case where the model is more or less solvable, is when the xij are complex quotients. This is called the Ginevra ensemble, and then there is an explicit distribution. There is an explicit expression for the eigenvalue distribution for finite n. So these are complicated formula, but maybe you can try to prove a central limit theorem. But I don't know. I don't think somebody has tried.